Okay, so now coming to the last two inference procedures for this unit are using two-sample t procedures for the difference of means. So first we're going to look at a two-sample t interval for the difference of means. Well, we know that we use confidence intervals to estimate the population parameter. Here, my population parameter is mu1 minus mu2. Of course, we'd have to define them both, but this is the true population difference of means between whatever your two quantitative variables are here. So we'll do that. The assumptions remain the same: stated random, independent, and normality by large counts. We have to check both populations separately, though, to ensure a normal model is appropriate overall, using one of these three scenarios here. If these conditions are met, we'll proceed by using a two-sample t interval for the difference of means. It has the following formula. Again, you don't have to memorize this because the general formula is provided to you on the AP Stats formula sheet at the bottom of the first page: confidence interval, statistic, critical value, standard error. So here, I'm going to be completely honest with you. There is a very snazzy formula to find the degrees of freedom. Typically we use n-1, but there's a little bit more mechanics to it when there are two samples. We're not going to learn that very snazzy formula, but for those of you who pursue higher statistics, you can come back and nerd out with me about that formula. But for the most part, we'll just pull it from the calculator, or if you don't have a calculator, we'll use the conservative approach, which means to take the smaller degrees of freedom from either sample size. And then, of course, the interpretations still remain the same. So we have a difference between our interval, which captures the population parameter, and then a difference of our confidence level, which deals with the procedure of these confidence intervals. And then if the claimed value falls within the confidence interval, there's no difference. It's not always zero. Or if it does not fall within the value, then we have significant evidence to conclude that there may be a difference. So let's go to one of the most infamous two-sample t intervals for means questions, which is 2009 FRQ number 4. Now, one of two fire stations in a certain town responds to calls in the northern half of the town, and the other fire station responds to calls in the southern half of the town. One of the town council members believes that the two fire stations have different mean response times, and response time is measured by the difference between the time an emergency call comes into the fire station and the time the first fire truck arrives on the scene. Data were collected to investigate whether the council member's belief is correct. A random sample of 50 calls selected from the northern fire station had a mean response of 4.3 and standard deviation of 3.7 minutes, and a separate random sample of 50 calls from the southern fire station had a mean response of 5.3 and a standard deviation of 3.2 minutes. So let's go ahead and construct and interpret a 95% confidence interval for the difference in mean response times between the two fire stations to see, is our council member's belief true that there is a difference? So let us proceed with this procedure here. But we need to first define our parameters. So in the first parameter here, I'm going to let mu of n be the true average, I'm going to abbreviate here, true average response time for the northern fire station. And these are our notes, so I'm being a little bit more sloppy, but if this were my AP exam, you bet I would be writing everything out. And we're going to check mu s, which is the true average response time for the south fire stations. Or sorry, only station. There's only one in each. Now, we have to check a few assumptions to ensure the validity of this process. And so our first assumption is that we must have an element of randomness. And here I have a random sample of 50 calls from the north fire station, and I have a random sample of 50 calls from the south fire station. Next, since the calls are going to two separate stations, I think it's safe to assume that the results will not influence one another. So since the calls are going to two separate stations, we can assume the calls are independent of one another. Actually, it'd be kind of weird, right, if the north fire station was like, hold, let me transfer you to the south fire station. Who knows? But for now, we can assume independence. And since we are sampling, we're going to need to check our 10% condition. And here, 50 would be 10% of 500. So you can either write the mathematical equality of 50 calls less than or equal to 10% of all calls, or we can say some fuzzy sentence like, we can assume there are at least 500 calls to the North Fire Station and 500 calls to the South Fire Station. So sampling without replacement is okay. And I don't know why I added that one, but just in case. You got to keep it spicy each time you check your assumptions. But because we're sampling from two separate populations, that's why they're independent. And because we're sampling less than 10% of their respective populations, the degree of dependence among our individual observations is also negligible. So I think we've met the independence criteria here. Now, the normal model, we weren't told anything about their populations, but we were told about their sample size. So here, the normal model is appropriate for both stations by the central limit theorem, since 50 is definitely greater than or equal to 30. And then I'm just going to put for both stations, just so they know I'm not being lazy. I do mean for both criteria here. Now, notice that I'm not just doing random check, independent check, 10% check, normal check. That means nothing. That is a check mark and a few words. Here, we have to elaborate on the assumptions, and anytime we run an inference procedure. And so you can see there's already context included. I know some information about my sample size, a little bit of information about the population from which I want to inference from. So this just gives the reader this idea that you are on track and you know what you're talking about here. And it would appear that since our conditions are met, we will use a two-sample t-interval for a difference in means. So notice there's always three components here, which is how many samples, 2 or 1, or matched, z or t. We use the normal model or the z statistic for proportions, because we know the population standard deviation or the standard error of the sampling distribution. Whereas we use t for quantitative data because we are now using our sample standard deviation to estimate the population standard deviation. So you have to distinguish z or t. And then a for statement. So is it for a population mean, for a population proportion, for a difference of means, difference of proportions, a mean difference, etc. So we've learned all of these different criteria now to put this together. So we've stated our parameters, checked our assumptions, and now we've communicated what we're going to do here for our t interval. And so now we would look something like this. And because it was not explicitly stated as to which department we were subtracting from, we're just going to go in order. So we're actually just going to go North Fire Station minus South Fire Station plus or minus t star times our standard error of the difference here. So the sample standard deviation for the north squared plus the sample standard deviation of the south squared divided by their respective sample sizes. Now what this looks like would be something along the lines of, let's go with 4.3 minus 5.3 plus or minus t star, and I'm going to leave it as t star here. The tomfoolery is too real, but we can find our degrees of freedom from the calculator. So the standard deviation here would be 3.7 squared over 50 plus this over 50, which is going to be 3.2. Okay, and this is going to give us the following interval from negative 2.373 up to 0.373. Now, my degrees of freedom will come to me from the calculator, and unfortunately, I do not have an applet to show you that. But in your calculator, you would go to a two-sample t interval, which for mine is option 0, and you'll just go ahead and put in your statistics here. So 4.3 for the mean, and 3.7 for the standard deviation, sample size 50, and then 5.3 for the mean, 3.2 standard deviation, other sample size 50. We're doing 95% confidence, no pool. And here, I get a wonky degrees of freedom of 96.0 004, and I'm going to let the person reading my response know that I got this from the calculator. I unfortunately do not know this fancy formula. But we've met all of the mechanics here, so we can actually now ensure this is a valid confidence interval, and we can interpret the interval. So it would sound something like, we are 95% confident the interval from negative 2.373 to 0.373, and here we're looking at the difference in response times, not the difference of calls, so this will be minutes, captures the true difference in means of response times for the north and south fire stations. Now, if I wanted some information about the confidence level, you would say something like, in repeated sampling of size 50, 95% of our constructed 95% confidence intervals from this population would capture the true difference of means of response times, etc. Now, based on our interval, does the interval support the belief that there is a difference in mean response time? So here, a little bit of math to this. Again, keep it spicy. Well, if north and south are equal to each other, this would mean zero would be in the interval. Now, if the north is greater than the south, then this would mean that the interval would be completely positive. And the last case here, if north was less than the south, then the interval would be completely negative. Now, we see that there's a negative-positive shift here, and that could only happen, we see that, well, 0 is actually in this interval. So do we have evidence to support that there is a difference? Actually, we do not have evidence because 0 is included in the confidence interval here, and 0 can only be included if the two mean response times are equal. So again, make sure you answer the question, give context, and give your reason why. So for this question, it would sound something like, no, the 95% confidence interval does not support the council member's belief that the two fire stations have different mean response times, since 0 minutes is included within the confidence interval. So something along those lines will do. Now, I've got some more practice questions for you here. So my students with the notes, you all can proceed to the next page. Random YouTube follower who stumbled upon this, go ahead and pause the video, read over the situation, and we'll go over the answers here in a bit. But go ahead and pause and take a look at these condition questions. Now, hopefully you were able to work through these, but if not, all good. We're going to go through this together. So we saw here that we are just testing the durability of cell phones by dropping them from different heights. We've selected random samples of 40 from each of the two manufacturers, and we have the following 90% confidence interval of 0.46 to 1.82 drops. So would the results of the study allow us to conclude a cause and effect relationship? Why or why not? And they would not. This is just a random sample of phones here, so I can reduce the bias. But really the only inference I can do here is I can generalize these results to the two manufacturers from which I've sampled. But I cannot infer cause and effect or that one has more durability than the other. I can simply infer association for those phones similar to the ones used in the study. Now our conditions are the same. We did random samples of 40 from both. So the normal model would be appropriate by the central limit theorem. It's safe to assume there's at least 400 phones from both manufacturers, and because we took the sample from two separate manufacturers, it's reasonable to assume that the durabilities of the phones would be independent of one another. In this interval, we are 90% confident the interval from 0.46 to 1.82 drops captures the true difference in the mean number of drops in the companies, testing their durability. Since 0 is not contained in this interval, there is actually evidence that we do have a difference in the phone types. And again, we have the situation. We did company 1 minus company 2. So each of these intervals here would give us a different insight into the durability of the phones. Well, here, since our interval was completely positive, we see that company 1 tends to have a higher durability than company 2. So that's just some more examples on how we would use a two-sample t-interval for the difference of means.